moving now to Sungwoo Lim. Are you there?
Yes, I'm here. Can you hear me?
We can, and you can go straight to your talk. Thank you.
Thank you. Thank you, everybody. My name is Sungwoo Lim, a research fellow at the Open University. Today, I'm going to talk about the microwave heating demonstrator payload on behalf of our Open University colleagues and Added Value Solutions UK Ltd and Viper RF. So why microwave heating? We are mainly focusing on binderless fabrication method. So when you think about binderless method, you could come up with solar concentrate and laser sintering and microwave heating. And all of these methods have their own pros and cons. And microwave has only requires around 23% of the energy compared with that of the laser sintering. And also it allows volumetric heating with a variable penetration depth by microwave frequency. But cons is it relies on the thermal runaway effect, especially when you are trying to heat and melting lunar regolith types of material, which has a very high melting point. In this case, it's more 1,150 Celsius degrees. So for industrial scale construction and resource beneficiation, we believe a microwave could offer a really high economic value, and that is why we are investigating microwave heating. But obviously, you can't just use a commercially available kitchen microwave for this purpose. So we have designed our own bespoke microwave and also manufactured it. And this is the current version we are working on at Open University. And I believe some of you already have seen this photo quite a number of times. So I'll just skip the detailed function here. And anyway, using that equipment, we've done lots of lab experiments and also microstructure analysis as well. We are currently using JSC1A, which is a lunar Mars simulant. And we heat the sample in the air condition with a variable input power. So when you heat the samples, when the thermal runaway occurs, you can instantly see the hot spot occurs. It looks like the video is not working. Does it work? It looks like the video doesn't work. Okay. Hot spot has occurred and it's continuously growing and sometimes split and moving around, trying to melting all the samples inside the crucibles. So when you slice the microwave the sample, you can see a big hollow on the top and quite dense molten part underneath. If you take a look more closely, you can see some distinctive areas like a fully molten area, partially molten area with a lot of air pockets, and also sintered area with the oxidized surface by the air in the cavity. And these areas has a specific features when you're looking at the microstructure level of details. So I told you we have tested with the various input power, and we've actually tried from 250 watt to 1,000 watt. And we found that this input power can be utilized for depending on any specific application. For example, if you're looking for the very solid construction component, you could go for over 800 watt because samples fabricated with this input power, it has up to 90 gigapascals of hardness. And if you're looking for the resource beneficiation, maybe you could go for lower input power, in this case, 250 watt. So if you look in the same image on the very top, very bottom right, there are quite a number of white spots there. Can you see that? And these white spots are actually spinner-like iron particles, which are extracted from the other minerals like olivine and pyroxene. So we have recently published our research findings to the Nature scientific report. And please do have a look at our papers if you are further interested in this microstructure stuff. By the way, whatever we have done and whatever we are currently doing, everything is actually simulation. Material is simulant, and the experiment environment is also simulated. And this is why we want to always do the proper microwave heating experiment on the real lunar surface using real lunar soil. So this is why we come up with the MHD payload idea, and we presented our idea to the Deep Space Gateway event at the ESA Aztec. It was back in 2017. And we said, well, if we put our payload on the moon surface, we could collect the regoliths and microwave the sample and continuously measure the temperature curves and also release the volatiles. And then we can send the data to the Earth for the analysis. And later we could also bring the microwave the samples for further microstructure analysis stuff. Well, since then, it's been a couple of years past now, and we are lucky to secure a couple of research grants from the UK Space Agency and also ESA as well. So first grant we received from UKSA, and we developed the initial concept of the MHD payload and also defined the essential component and the subsystems, as you can see here. For example, like number one is a sample collector, number two is a microwave cavity, number 6 is a mass spectrometer, and number 3 is a crucible transport field. After completing this project, we secured another follow-on project from the same funder. And during this project, we are mainly focused on improving the cavity design and functionality, and also heating performance as well. And we also updated the sub-functions of the cavity accordingly, and also recently changed the sample collection mechanisms, and also replaced this crucible transport field to the more simplified robotic arm version, and added a rack storage function. So we effectively increased our crucible capacity from 3 to 5. And this project was actually completed last month. And from this month, we are actually starting the ESA's Open Earth manufacturing and construction project. And this project is for 18 months. And during this project, we are mainly focusing on to detail the entire more efficient package of the overall payload. And because we are recently changed the sample collection mechanism, we're going to do also trade-off analysis as well. And we also add oxygen and water extraction unit, including the cold fingers, which directly connect to our mass spectrometer. And we will design final form factor of the rest of the subsystem, which you can see here, like an orange box, which include power supply unit and computer systems, etc., and data log as well. We are also continuously doing computational simulation to improve the heating performance of the microwave cavity as well. So we've done quite a number of design iteration, and each iteration we are trying to identify the numbers and positions and even the strengths of the hotspots, and try to understand when the thermal runaway actually occurs, how the temperature is changed inside of a sample, and also whether the electric field of the sample is changed by temperature or not. So far, we have learned is when the sample temperature exceeds 800 Kelvin, the electric field of the sample is dramatically reduced, as you can see from the right side of the plot. And this is because of the material properties of the lunar regolith, especially for electrical conductivity, which increased exponentially by temperature. And also because of the resonant frequency of the cavity is also changed. So we are trying to continuously shifting the resonant frequency, trying to mitigate this phenomenon as well. And lastly, we continuously monitoring the hotspot positions and the excessive heat transfer cases as well. So when you see this case, the hotspot actually starting from the core of the sample, but later it moved down to the bottom of the crucible, which causes excessive heat transfer to our subsystems. So in this case, we have to come up with a more efficient thermal management strategy. So those things are needed, used for simulation. And at the end of this project, I mean the ESA project, we will build a breadboard of the MHD payload and try to secure another grant for developing the prototype and the space-qualified flight unit, which is ready to be deployed on the lunar surface to do the more accurate microwave heating experiment. So this is the last slide. Apart from the MHD payload development activity, we are also developing microwave heating-based 3D printing demonstrator payload as well. And this MI3DP payload requires a much higher input power. So we are collaborating with our industrial partner, Viper, trying to study the concept architecture of the 1 kilowatt solid state of power amplifier, which is the microwave generator. So yeah, these are the things that we are currently working on in parallel. And if you are interested in our payload development activities and also looking for future collaboration, please do contact us. Thank you for listening.
Thank you very much, Sungwoo.